Video 33 of the master course Quantum Chemistry of Molecular Electromagnetic Properties. The topic of this lecture is potential energy in a magnetic induction. Now, like for the electric case in the last chapter, we want to now look at the energy of our, now here, current distribution J in the presence of an external magnetic induction. And we're going to look at a homogeneous magnetic induction. The expression for the energy is again rather similar to the one for the electric case, where we had a product of the charge density and the electrostatic scalar potential. Now we have a product of the current density and the vector potential, and both being vectors, we have the scalar or dot product of them and then integrated over the whole space. And AB, our vector potential, is now the vector potential corresponding to this homogeneous magnetic induction, where the magnetic induction is defined as the curl of this vector potential. Here, because we are looking at the static case, no time dependence. We had previously the expression for the time dependent case. Now again, we're going to expand now. We're going to expand this vector potential here now in a Taylor series expansion around, again, around an origin, around the gauge origin GO. So in the first term, we have the value of the vector potential at this expansion point, and then we get the first derivative multiplied with how far away from the expansion point we are. The usual Taylor series expansion of any function, except this is, of course, a vector. Now inserting this in the, inserting here this expansion up there in our expression for the energy of the current density in this vector potential, we get these terms here, and I'll write the first two terms up again, and we end, like in the case for the electric situation, we end up with the same integrals over the current density as we had before. Here just a component of the current density, and we know this is 0, so this term is 0 because there is no magnetic monopoles, and this term we can again rewrite in terms of the magnetic dipole moment. So in first place, we rewrite it in terms of the antisymmetric part of that, because the symmetric we could show earlier in the last lecture that this one is 0. So we have a derivative of a component of the vector potential, and here we have this antisymmetric product of the current density and a position vector, which we can remember from before, of course, is the magnetic dipole moment. And looking at all the indices, one can see that one can write this in vector notation, actually as the curl of the vector potential, scalar product here with our magnetic dipole moment, which means the first term is actually the product of, because the curl of the vector potential was the homogeneous magnetic field, so the homogeneous magnetic field at our gauge origin at the expansion, and the integral which is left here then is our magnetic dipole moment from before. So the energy is actually the energy of a current distribution in external magnetic field. The first term is actually the dipole interaction term. So we have the magnetic dipole moment times the magnetic induction and the minus sign before. So we actually get a similar term to what we had in the electric case. Which also means that we can, from this expression, we can actually write a definition for a component of the magnetic dipole moment as the derivative of the energy in the presence of the field, so the field-dependent energy, with respect to a component of the field and a minus sign. An expression which is completely analogous to the one which we had for the electric dipole moment, where we had the electric field, where we had the energy in the presence of an electric field and the derivative of this energy with respect to a component of the field. Here we have the same, precisely the same, with respect to the magnetic dipole moment.